Flerovium. Flerovium is a superheavy artificial chemical element with symbol fluid and atomic number 114. It is an extremely radioactive synthetic element. The element is named after the Flerov Laboratory of Nuclear Reactions of the Joint Institute for Nuclear Research in Dubna, Russia, where the element was discovered in 1998. The name of the laboratory, in turn, honors the Russian physicist Georgy Flyorov. The name was adopted by IUPAC on May 30, 2012. In the periodic table of the elements, it is a transactinide element in the p block. It is a member of the 7th period and is the heaviest known member of the carbon group. It is also the heaviest element whose chemistry has been investigated. Initial chemical studies performed in 2007-2008 indicated that Flerovium was unexpectedly volatile for a group 14 element. In preliminary results, it even seemed to exhibit properties similar to those of the noble gases. More recent results show that Flerovium's reaction with gold is similar to that of copernicium, showing that it is a very volatile element that may even be gaseous at standard temperature and pressure, that it would show metallic properties, consistent with it being the heavier homologue of lead, and that it would be the least reactive metal in group 14. The question of whether Flerovium behaves more like a metal or a noble gas is still unresolved as of 2018. About 90 atoms of Flerovium have been observed, 58 were synthesized directly, and the rest were made from the radioactive decay of heavier elements. All of these Flerovium atoms have been shown to have mass numbers from 284 to 290. The most stable known Flerovium isotope, Flerovium 289, has a half-life of around 2.6 seconds, but it is possible that the unconfirmed Flerovium 290 with one extra neutron may have a longer half-life of 19 seconds. This would be one of the longest half-lives of any isotope of any element at these farthest reaches of the periodic table. Flerovium is predicted to be near the center of the theorized island of stability, and it is expected that heavier Flerovium isotopes, especially the possibly doubly magic Flerovium 298, may have even longer half-lives. From the late 1940s to the early 1960s, the early days of the synthesis of heavier and heavier transuranium elements, it was predicted that since such heavy elements did not occur naturally, they would have shorter and shorter half-lives to spontaneous fission, until they stopped existing altogether at around element 108. Initial work in the synthesis of the actinides appeared to confirm this. The nuclear shell model, introduced in the late 1960s, stated that the protons and neutrons formed shells within a nucleus, somewhat analogous to electrons forming electron shells within an atom. The noble gases are unreactive due to their having full electron shells, thus it was theorized that elements with full nuclear shells having so-called magic numbers of protons or neutrons would be stabilized against radioactive decay. A doubly magic isotope, having magic numbers of both protons and neutrons, would be especially stabilized, and it was calculated that the next doubly magic isotope after lead 208 would be Flerovium 298 with 114 protons and 184 neutrons, which would form the center of a so-called island of stability. This island of stability, supposedly ranging from copernicium to oganesson, would come after a long sea of instability from elements 101 to 111, and the Flerovium isotopes in it were speculated in 1966 to have half-lives in excess of 100 million years. These early predictions fascinated researchers, and led to the first attempted synthesis of Flerovium in 1968 using the reaction 248 cm. No isotopes of Flerovium were found in this reaction. This was thought to occur because the compound nucleus 288Fl only has 174 neutrons instead of the hypothesized magic 184, and this would have a significant impact on the half-life and cross-section of such a reaction. It then took 30 more years for the first isotopes of Flerovium to be synthesized. More recent work suggests that the local islands of stability around hassium and Flerovium are due to these nuclei being respectively deformed and oblate, which make them resistant to spontaneous fission, and that the true island of stability for spherical nuclei occurs at around unbibium 306. Flerovium was first synthesized in December 1998 by a team of scientists at the Joint Institute for Nuclear Research in Dubna, Russia, led by Yuri Oganessian, who bombarded a target of plutonium-244 with accelerated nuclei of calcium-48. This reaction had been attempted before, but without success. For this 1998 attempt, the JINR had upgraded all of its equipment to detect and separate the produced atoms better and bombard the target more intensely. A single atom of Flerovium, decaying by alpha emission with a lifetime of 30.4 seconds, was detected. The decay energy measured was 9.71 MeV, giving an expected half-life of 223 s. This observation was assigned to the isotope Flerovium-289 and was published in January 1999. The experiment was later repeated, but an isotope with these decay properties was never found again, and hence the exact identity of this activity is unknown. It is possible that it was due to the metastable isomer 289-MFL, but because the presence of a whole series of longer-lived isomers in its decay chain would be rather doubtful, the most likely assignment of this chain is to the 2N channel leading to 290FL and electron capture to 290NH, which fits well with the systematics and trends across Flerovium isotopes, and is consistent with the low beam energy that was chosen for that experiment, although further confirmation would be desirable via the synthesis of 294LV in the 248 cm reaction, which would alpha decay to 290FL. The team at Riken reported a possible synthesis of the isotopes 294LV and 290FL in 2016 through the 248 cm reaction, but the alpha decay of 294LV was missed. Alpha decay of 290FL to 286CN was observed instead of electron capture to 290NH. And the assignment to 294LV instead of 293LV and decay to an isomer of 285CN was not certain. Glenn T. Seaborg, a scientist at the Lawrence Berkeley National Laboratory who had been involved in work to synthesize such superheavy elements, had said in December 1997 that one of his longest-lasting and most cherished dreams was to see one of these magic elements. He was told of the synthesis of Flerovium by his colleague Albert Ghiorso soon after its publication in 1999. Ghiorso later recalled, "I wanted Glenn to know, so I went to his bedside and told him. I thought I saw a gleam in his eye, but the next day when I went to visit him he didn't remember seeing me. As a scientist, he had died when he had that stroke." Seaborg died 2 months later, on February 25, 1999. In March 1999, the same team replaced the 244Pu target with a 242Pu1 in order to produce other Flerovium isotopes. This time 2 atoms of Flerovium were produced, decaying via alpha emission with a half-life of 5.5 s. They were assigned as 287FL. This activity has not been seen again either, and it is unclear what nucleus was produced. It is possible that it was the metastable isomer 287MFL or the result of an electron capture branch of 287FL leading to 287NH and 283RG. The now confirmed discovery of Flerovium was made in June 1999 when the Dubna team repeated the first reaction from 1998. This time, 2 atoms of Flerovium were produced. They alpha decayed with a half-life of 2.6 s, different from the 1998 result. This activity was initially assigned to 288FL in error, due to the confusion regarding the previous observations that were assumed to come from 289FL. Further work in December 2002 finally allowed a positive reassignment of the June 1999 atoms to 289FL. In May 2009, the Joint Working Party of IUPAC published a report on the discovery of copernicium in which they acknowledged the discovery of the isotope 283CN. This implied the discovery of Flerovium, from the acknowledgement of the data for the synthesis of 287FL and 291LV, which decay to 283CN. The discovery of the isotopes Flerovium 286 and -287 was confirmed in January 2009 at Berkeley. This was followed by confirmation of Flerovium 288 and -289 in July 2009 at the Gesellschaft für Schwerionenforschung in Germany. In 2011, IUPAC evaluated the Dubna team experiments of 1999-2007. They found the early data inconclusive, but accepted the results of 2004-2007 as Flerovium, and the element was officially recognized as having been discovered. While the method of chemical characterization of a daughter was successful in the cases of Flerovium and Livermorium, and the simpler structure of even nuclei made the confirmation of oganescence straightforward, there have been difficulties in establishing the congruence of decay chains from isotopes with odd protons, odd neutrons, or both. To get around this problem with hot fusion, the decay chains from which terminate in spontaneous fission instead of connecting to known nuclei as cold fusion allows, experiments were performed at Dubna in 2015 to produce lighter isotopes of Flerovium in the reactions of 48Ca with 239Pu and 240Pu, particularly 283Fl, 284Fl, and 285Fl. The last had previously been characterized in the 242Pu 285Fl reaction at the Lawrence Berkeley National Laboratory in 2010. The isotope 285Fl was more clearly characterized, while the new isotope 284Fl was found to undergo immediate spontaneous fission instead of alpha decay to known nuclides around the n equals 162 shell closure, and 283Fl was not found. This lightest isotope may yet conceivably be produced in the cold fusion reaction 208Pb283Fl, which the team at Riken in Japan has considered investigating. This reaction is expected to have a higher cross-section of 200 Fb than the world record low of 30 Fb for 209 by 278 Nh, the reaction which Riken used for the official discovery of element 113, now named nihonium. The Dubna team repeated their investigation of the 240Pu plus 48Ca reaction in 2017, observing 3 new consistent decay chains of 285Fl, an additional decay chain from this nuclide that may pass through some isomeric states in its daughters, a chain that could be assigned to 287Fl, and some spontaneous fission events of which some could be from 284Fl, though other interpretations including side reactions involving the evaporation of charged particles are also possible. Using Mendeleev's nomenclature for unnamed and undiscovered elements, Flerovium is sometimes called EKA lead. In 1979, IUPAC published recommendations according to which the element was to be called ununquadium, a systematic element name as a placeholder, until the discovery of the element is confirmed and a permanent name is decided on. Most scientists in the field called it element 114, with the symbol of E114 or 114. According to IUPAC recommendations, the discoverer of a new element has the right to suggest a name. After the discovery of Flerovium and Livermorium was recognized by IUPAC on June 1, 2011, IUPAC asked the discovery team at the JINR to suggest permanent names for those 2 elements. The Dubna team chose to name element 114 Flerovium, after the Russian Flerov laboratory of nuclear reactions, named after the Soviet physicist Georgy Flyorov. Earlier reports claim the element name was directly proposed to honor Flerov. In accordance with the proposal received from the discoverers, IUPAC officially named Flerovium after the Flerov laboratory of nuclear reactions, not after Flerov himself. Flerov is known for writing to Joseph Stalin in April 1942 and pointing out the silence in scientific journals in the field of nuclear fission in the United States, Great Britain, and Germany. Flerov deduced that this research must have become classified information in those countries. Flerov's work and urgings led to the development of the USSR's own atomic bomb project. Flerov is also known for the discovery of spontaneous fission with Konstantin Petržak. The naming ceremony for Flerovium and Livermorium was held on October 24, 2012 in Moscow. The physical basis of the chemical periodicity governing the periodic table is the electron shell closures at each noble gas, as any further electrons must enter a new shell with higher energy. Closed shell electron configurations are markedly more stable, leading to the relative inertness of the noble gases. Since protons and neutrons are also known to arrange themselves in closed nuclear shells, the same effect happens at nucleon shell closures, which happen at specific nucleon numbers often dubbed magic numbers. The known magic numbers are 2, 8, 20, 28, 50, and 82 for protons and neutrons, and additionally 126 for neutrons. Nucleons with magic proton and neutron numbers, such as helium-4, oxygen-16, calcium-48, and lead-208, are termed doubly magic and are very stable against decay. This property of increased nuclear stability is very important for superheavy elements. Without any stabilization, their half-lives would be expected by exponential extrapolation to be in the range of nanoseconds when element 110 is reached, because of the ever-increasing repulsive electrostatic forces between the positively charged protons that overcome the limited-range strong nuclear force that holds the nucleus together. The next closed nucleon shells and hence magic numbers are thought to denote the center of the long-sought island of stability, where the half-lives to alpha decay and spontaneous fission lengthen again. Initially, by analogy with the neutron magic number 126, the next proton shell was also expected to occur at element 126, too far away from the synthesis capabilities of the mid-20th century to achieve much theoretical attention. In 1966, new values for the potential and spin-orbit interaction in this region of the periodic table contradicted this and predicted that the next proton shell would occur instead at element 114, and that nuclides in this region would be as stable against spontaneous fission as many heavy nuclei such as lead-208. The expected closed neutron shells in this region were at neutron number 184 or 196, thus making 298Fl and 310Fl candidates for being doubly magic. 1972 estimates predicted a half-life of about a year for 298Fl, which was expected to be near a large island of stability with the longest half-life at 294ds. After the synthesis of the first isotopes of elements 112 through 118 at the turn of the 21st century, it was found that the synthesized neutron-deficient isotopes were stabilized against fission. In 2008 it was thus hypothesized that the stabilization against fission of these nuclides was due to their being oblate nuclei, and that a region of oblate nuclei was centered on 288Fl. Additionally, new theoretical models showed that the expected gap in energy between the proton orbitals 2f7/2 and 2f5/2 was smaller than expected, so that element 114 no longer appeared to be a stable spherical closed nuclear shell. The next doubly magic nucleus is now expected to be around 306 UBB, but the expected low half-life and low production cross-section of this nuclide makes its synthesis challenging. Nevertheless, the island of stability is still expected to exist in this region of the periodic table, and nearer its center some nuclides, such as 291MC and its alpha and beta decay daughters, may be found to decay by positron emission or electron capture and thus move into the center of the island. Due to the expected high fission barriers, any nucleus within this island of stability decays exclusively by alpha decay and perhaps some electron capture and beta decay, both of which would bring the nuclei closer to the beta stability line where the island is expected to be. Electron capture is needed to reach the island, which is problematic because it is not certain that electron capture becomes a major decay mode in this region of the chart of nuclides. Several experiments have been performed between 2000 and 2004 at the Flerov Laboratory of Nuclear Reactions in Dubna studying the fission characteristics of the compound nucleus 292Fl by bombarding a plutonium-244 target with accelerated calcium-48 ions. A compound nucleus is a loose combination of nucleons that have not yet arranged themselves into nuclear shells. It has no internal structure and is held together only by the collision forces between the target and projectile nuclei. The results revealed how nuclei such as this fission predominantly by expelling doubly magic or nearly doubly magic fragments such as calcium-40, tin-132, lead-208, or bismuth-209. It was also found that the yield for the fusion-fission pathway was similar between calcium-48 and iron-58 projectiles, indicating a possible future use of iron-58 projectiles in superheavy element formation. It has also been suggested that a neutron-rich Flerovium isotope can be formed by the quasi-fission of a massive nucleus. Recently it has been shown that the multi-nucleon transfer reactions in collisions of actinide nuclei might be used to synthesize the neutron-rich superheavy nuclei located at the island of stability, although production of neutron-rich nobelium or seaborgium nuclei is more likely. Theoretical estimation of the alpha decay half-lives of the isotopes of the Flerovium supports the experimental data. The fission-survived isotope 298Fl, long expected to be doubly magic, is predicted to have alpha decay half-life around 17 days. The direct synthesis of the nucleus 298Fl by a fusion evaporation pathway is currently impossible since no known combination of target and stable projectile can provide 184 neutrons in the compound nucleus, and radioactive projectiles such as calcium-50 cannot yet be used in the needed quantity and intensity. Currently, one possibility for the synthesis of the expected long-lived nuclei of copernicium and Flerovium near the middle of the island include using even heavier targets such as curium-250, berkelium-249, californium-251, and einsteinium-254, that when fused with calcium-48 would produce nuclei such as 291Mc and 291Fl, with just enough neutrons to alpha decay to nuclides close enough to the center of the island to possibly undergo electron capture and move inwards to the center, though the cross-sections would be small and little is yet known about the decay properties of superheavy nuclides near the beta stability line. This may be the best hope currently to synthesize nuclei on the island of stability, but it is speculative and may or may not work in practice. Another possibility is to use controlled nuclear explosions to achieve the high neutron flux necessary to create macroscopic amounts of such isotopes. This would mimic the R process in which the actinides were first produced in nature and the gap of instability after polonium bypassed, as it would bypass the gaps of instability at 258-260 Fm and at mass number 275. Some such isotopes may even have been synthesized in nature, but would have decayed away far too quickly and be produced in far too small quantities to be detectable as primordial nuclides today outside cosmic rays. Flerovium is a member of group 14 in the periodic table, below carbon, silicon, germanium, tin, and lead. Every previous group 14 element has 4 electrons in its valence shell, forming a valence electron configuration of ns2np2. In Flerovium's case, the trend will be continued and the valence electron configuration is predicted to be 7s27p2. Flerovium will behave similarly to its lighter congeners in many respects. Differences are likely to arise. A largely contributing effect is the spin-orbit interaction, the mutual interaction between the electron's motion and spin. It is especially strong for the superheavy elements, because their electrons move faster than in lighter atoms, at velocities comparable to the speed of light. In relation to Flerovium atoms, it lowers the 7s and the 7p electron energy levels, but 2 of the 7p electron energy levels are stabilized more than the other 4. The stabilization of the 7s electrons is called the inert pair effect, and the effect tearing the 7p subshell into the more stabilized and the less stabilized parts is called subshell splitting. Computation chemists see the split as a change of the second quantum number L from 1 to 12 and 32 for the more stabilized and less stabilized parts of the 7p subshell, respectively. For many theoretical purposes, the valence electron configuration may be represented to reflect the 7p subshell split as 7s27p21/2. These effects cause Flerovium's chemistry to be somewhat different from that of its lighter neighbors. Due to the spin-orbit splitting of the 7p subshell being very large in Flerovium, and the fact that both Flerovium's filled orbitals in the 7th shell are stabilized relativistically, the valence electron configuration of Flerovium may be considered to have a completely filled shell, making Flerovium a very noble metal. Its first ionization energy of 8.539 eV should be the highest in group 14. The 6d electron levels are also destabilized, leading to some early speculations that they may be chemically active, although newer work suggests that this is unlikely. The closed shell electron configuration of Flerovium results in the metallic bonding in metallic Flerovium being weaker than in the preceding and following elements. Thus, Flerovium is expected to have a low boiling point, and has recently been suggested to be possibly a gaseous metal, similar to the predictions for copernicium, which also has a closed shell electron configuration. The melting and boiling points of Flerovium were predicted in the 1970s to be around 70 degrees C and 150 degrees C, significantly lower than the values for the lighter group 14 elements, and continuing the trend of decreasing boiling points down the group. Although earlier studies predicted a boiling point of 1000 degrees C or 2840 degrees C, This is now considered unlikely because of the expected weak metallic bonding in Flerovium, and that group trends would expect Flerovium to have a low sublimation enthalpy. Recent experimental indications have suggested that the pseudo-closed shell configuration of Flerovium results in very weak metallic bonding, and hence that Flerovium is probably a gas at room temperature with a boiling point of around 60 degrees C. Like mercury, radon, and copernicium, but not lead and oganesson, Flerovium is calculated to have no electron affinity. In the solid state, Flerovium is expected to be a dense metal due to its high atomic weight, with the density variously predicted to be either 22G/cm3 or 14G/cm3. Flerovium is expected to crystallize in the face-centered cubic crystal structure like that of its lighter congener lead, although earlier calculations predicted a hexagonal close-packed crystal structure due to spin-orbit coupling effects. The electron of the hydrogen-like Flerovium ion is expected to move so fast that it has a mass 1.79 times that of a stationary electron, due to relativistic effects. For comparison, the figures for hydrogen-like lead and tin are expected to be 1.25 and 1.073 respectively. Flerovium would form weaker metal-metal bonds than lead and would be adsorbed less on surfaces. Flerovium is the heaviest known member of group 14 in the periodic table, below lead, and is projected to be the second member of the 7p series of chemical elements. Nihonium and Flerovium are expected to form a very short subperiod, coming between the filling of the 6d5/2 and 7p1/2 subshells. Their chemical behavior is expected to be very distinctive. Nihonium's homology to thallium has been called doubtful by computational chemists, while Flerovium's to lead has been called only formal. The first 5 members of group 14 show the group oxidation state of +4, and the latter members have an increasingly prominent +2 chemistry due to the onset of the inert pair effect. Tin represents the point at which the stability of the +2 and +4 states are similar, and lead is the most stable of all the chemically well understood group 14 elements in the +2 oxidation state. The 7s orbitals are very highly stabilized in Flerovium, and thus a very large sp3 orbital hybridization is required to achieve the +4 oxidation state, so Flerovium is expected to be even more stable than lead in its strongly predominant +2 oxidation state, and its +4 oxidation state should be highly unstable. For example, Flerovium dioxide is expected to be highly unstable to decomposition into its constituent elements, and Flerovane, which should have FLH bond lengths of 1.787A, is predicted to be more thermodynamically unstable than plumbane, spontaneously decomposing into Flerovium hydride and hydrogen gas. Flerovium tetrafluoride would have bonding mostly due to SD hybridizations rather than sp3 hybridizations, and its decomposition to the difluoride and fluorine gas would be exothermic. The gross destabilization of all the tetrahalides is unfortunate because otherwise these compounds would be very useful in gas phase chemical studies of Flerovium. The corresponding polyfluoride anion FLF26 should be unstable to hydrolysis in aqueous solution, and Flerovium polyhalide anions such as FLBr3 and FLI3 are predicted to form preferentially in Flerovium-containing solutions. The SD hybridizations were suggested in early calculations as the 7s and 6d electrons in Flerovium share approximately the same energy, which would allow a volatile hexafluoride to form, but later calculations do not confirm this possibility. In general, the spin-orbit contraction of the 7p1/2 orbital should lead to smaller bond lengths and larger bond angles. This has been theoretically confirmed in FLH2. Nevertheless, even FLH2 should be relativistically destabilized by 2.6 eV to below FL and H2. The large spin-orbit effects also break down the usual singlet-triplet divide in the group 14 dihydrides. FLF2 and FLCl2 are predicted to be more stable than FLH2. Due to the relativistic stabilization of Flerovium's 7s27p21/2 valence electron configuration, the zero oxidation state should also be more stable for Flerovium than for lead, as the 7p1/2 electrons begin to also exhibit a mild inert pair effect. This stabilization of the neutral state may bring about some similarities between the behavior of Flerovium and the noble gas radon. Due to the expected relative inertness of Flerovium, its diatomic compounds FLH and FLF should have lower energies of dissociation than the corresponding lead compounds PBH and PBF. Flerovium should be even more electronegative than lead. Lead has electronegativity 2.33 on the Pauling scale, the lead value is only 1.87. Flerovium should be more stable than lead, and polyhalide ions and compounds of types FLX+, FLX2, FLX3, and FLX24 are expected to form readily. The fluorides would undergo strong hydrolysis in aqueous solution. All the Flerovium dihalides are expected to be stable, with the difluoride being water-soluble. Spin-orbit effects would destabilize Flerovium dihydride by almost 2.6 eV. In solution, Flerovium would also form the oxoanion flerovite in aqueous solution, analogous to plumbite. Flerovium sulfate and sulfide should be very insoluble in water, and Flerovium acetate and nitrate too, should be quite water-soluble. The standard electrode potential for the reduction of Fl2+ ions to metallic Flerovium is estimated to be around plus 0.9 V, confirming the increased stability of Flerovium in the neutral state. In general, due to the relativistic stabilization of the 7p1/2 spinor, Fl2+ is expected to have properties intermediate between those of Hg2+ or Cd2+ and its lighter congener Pb2+. Flerovium is currently the heaviest element to have had its chemistry experimentally investigated, although the chemical investigations have so far not led to a conclusive result. 2 experiments were performed in April-May 2007 in a joint FLNR-Sci collaboration aiming to study the chemistry of copernicium. The first experiment involved the reaction 242Pu287Fl and the second the reaction 244Pu288Fl. These reactions produced short-lived Flerovium isotopes whose copernicium daughters would then be studied. The adsorption properties of the resultant atoms on a gold surface were compared with those of radon, as it was then expected that copernicium's full shell electron configuration would lead to noble gas-like behavior. Noble gases interact with metal surfaces very weakly, which is uncharacteristic of metals. The first experiment allowed detection of 3 atoms of 283Cn but also seemingly detected 1 atom of 287Fl. This result was a surprise given the transport time of the product atoms is 2s, so the Flerovium atoms produced should have decayed to copernicium before adsorption. In the second reaction, 2 atoms of 288Fl and possibly 1 atom of 289Fl were detected. 2 of the 3 atoms displayed adsorption characteristics associated with a volatile, noble gas-like element, which has been suggested but is not predicted by more recent calculations. These experiments provided independent confirmation for the discovery of copernicium, Flerovium, and livermorium via comparison with published decay data. Further experiments in 2008 to confirm this important result detected a single atom of 289Fl, and supported previous data showing Flerovium having a noble gas-like interaction with gold. The experimental support for a noble gas like Flerovium soon weakened. In 2009 and 2010, the FLNR-Sci collaboration synthesized further atoms of Flerovium to follow up their 2007 and 2008 studies. In particular, the first 3 Flerovium atoms synthesized in the 2010 study suggested again a noble gas-like character, but the complete set taken together resulted in a more ambiguous interpretation, unusual for a metal in the carbon group but not fully like a noble gas in character. In their paper, the